4 chapters. Yeah.
That's perfect. Like 3 days. That's good. That's perfect timing.
Not 3 days. It's the exam, right?
Yeah.
2 days.
Yeah, that's perfect. That's right, Sarah.
No excuses.
That's how it always works. They throw so much in this class, it's crazy how much they do here. Most schools I teach at this class is like broken up into 2 classes. You do like chapters 1 through 9 in a semester, and they do like the organic and all that stuff.
We'll have 5. Why did they do that?
Because they have finals week, so they do it like weird time. I don't know where to that.
Both they do, right? Is they have a master Chem when there's nothing.
Yeah, because yeah, so you're not. They're supposed to do it so nobody ever crosses over into like you have conflict in your finals and stuff like that.
What would you say the finals did
I say the highlights of a lot of the stuff we talked about up through the chapter. So obviously not everything. Unless you plan on camping out here for like 4 weeks or something like that. But I would say though it is going to be pretty comprehensive over all the chapters. So there might feel like there's maybe more questions on the last few because we haven't taken an exam on it, but it definitely will cover all the highlights of the earlier chapters of like nomenclature, Lewis structures, conversions, all that kind of stuff. And so there'll definitely be a question like that.
I like that.
There you go.
It's the same format.
It will be. There will be a multiple choice part in kind of like a. That's what happens when computer programmers write the homework.
Why is shipping crazy? All right, right? So what makes it simple? What do you have? The OA. And the OA, hold on. That would be. Okay. So, and then 3 methyl. Or is that in 3? And 3 methyl. And yeah. Is there a one to go here? No. Right, because earlier you said. Yeah. Okay. Okay. So down the click. Click. Okay, so then you're looking at. Why is it double? Oh, one of the word is. Oh no, it's not a double. this one here, right? And did it there's your brain. Better. Yeah, I like what? Okay. And then, so where are you putting it? Where do you so which direction? Okay. So what you do is you drink that.
Okay, we're going to, as it says there, we're gonna go to chapter 14, which is the last chapter of organic, and we will come back to 13 for a little carbohydrates afterwards. So pretty much in this chapter, we're going to cover everybody that's left in organic land here, which is carbohydrate. No, we already did not. That was 13. Carboxylic acids, esters, amines, and amides here. So a couple more oxygen-containing guys and some nitrogen-containing groups here with our amines and our amides. All right. So we're going to start with carboxylic acids, which we touched upon in the previous chapter as we saw our formation of a primary alcohol. I can do a, and we're carboxylic acid group there as we go across there. So our carboxylic acid group, actually, our carboxylic group is sometimes referred to, actually contains two sort of groups that are important. It has that carbonyl carbon, so it has that, which has contains two polar groups on it, which gives us some important sort of properties that we'll talk about. As we sort of talked about and touched upon when we were doing the sort of oxidation of aldehydes to carboxylic acids, basically we just kind of dropped the E from the alkane name and put oic acid basically the end of it when we go to name it. So this guy here, which has basically 1 and 2 carbons, which is based off of ethane. Drop that E, put oic acid, and now you have ethanoic acid, which is the name of that. It also has a common name, which is acetic acid, and that's again the major component of vinegar, actually, that particular one there. Here we have and 2 carbons, and that's based off of and that will get you your propanoic acid. And here, this actually carboxylic acid group. Now you can see on the benzene ring, the actual carboxylic acid group, like part of the ring. So that group kind of comes right off of it there. So we do go with oic acid there. In addition, this functional group will be at the end of the molecule, kind of like aldehydes, because of this hydrogen. So that functional group has to be at one end versus the other. That also usually means that you do not need to do any numbering of where it's located but it will be carbon number 1, where this carbon oxygen double bond is located for anybody else that may be attached. So as I said there, basically we're just going to drop the E, put oic acid, and again, you don't need to give the location because it should be at the end, but for numbering purposes, this will be definitely carbon number 1, wherever that carbon oxygen double bond is. Even though I wrote a 2 there, that would be carbon number 1 on that. It's like 2, but not so much. So here we have 1 carbon, which is based off of methane. Kind of drop the methane E part of it and put oic acid. So methanoic acid, ethanoic acid, propanoic acid, basically put that at the end. Again, anything else would be numbered or named in alphabetical order. But again, numbering wise, we still do give it the priority. So it should always be 1, basically, that carbon oxygen double bond. So here we can see we have basically 1, 2, 3, and 4, or if you want to go upwards as well. But it is 4, which is based off of butane. It has our there. Once again, we don't need to give the location of this, but it definitely is going to be carbon number 1, and that is why we get down to butane acid in terms of the name. Here, once again, benzene ring, along with this part here, the benzoic acid part of it. So that's all basically together, if you will. Once again, where the carbon is attached in this particular case in the ring should be carbon number 1. And then obviously we'd want to give these guys the smallest numbering. So going clockwise here will do that. Obviously, we went counterclockwise, we would get a larger number. And here we have 2 chlorine groups, which is where the dichloral part comes. And again, our numbering are 2 and our 3. So we get our 2,3 dichloral benzoic acid. Any questions on that there? All right, so here's some of the names and some common names. I would say probably out of these 4 common names here, the 2 that you should probably have some familiarity with because they are used a lot. And I would say formic acid and acetic acid are still used a lot for methanoic acid and ethanoic acid. So definitely acetic acids are used a lot. And actually, I would say probably more people use maybe acetic acid than ethanoic acid. But again, you should have that relationship of what these guys are. So I would say for us, these 2, you definitely should maybe know the common names. Again, because sometimes they will definitely use them along the way. So a red instinct, for example, is formic acid, which is again methanoic acid. So formic acid is methanoic acid, 1 carbon based off of methane, methanoic acid here. And as I mentioned before, acetic acid, which is really the main component of vinegar, has 2 carbons, which is based off of ethane, and ethanoic acid is also used. So again, these 2 probably should have that sort of familiarity of common name and also IUPAC way of naming. All right, so why don't you name this guy? Why don't you also give the name for, let's see this guy here. Okay, so let's take a look. We'll start with the first one here. So just count up some carbons here. 1, 2, 3, 4, and 5. We do have our carboxylic acid group right there. That's a carbon double bonded to an oxygen with an OH. So 5 is based off of pentane, and since it is a carboxylic acid, this will be pentanoic acid. Remember that we don't need to give the location of where that carbon oxygen double bond is, but it definitely will be carbon number 1. And that means that carbon number 2, we have our group hanging out here which is just a methyl group as there's nothing written there. So this would be a little 2-methyl pentanoic acid. Any questions on that one there? Coming to our next one, we got looks like 1, 2, 3, 4, 5. We could also get 5 by going 1, 2, 3, 4, and then coming down for 5. Again, it could go either way. Like other, it should give you really the same name. I'm just going to take the straight one there. In addition to that, we got a group here, and we do have a group there. Here looks like the same number of carbons, so obviously we still have our carboxylic acid group right there. By the way, sometimes this carboxylic acid H in formula, something like that. So if you do see a like COOH written molecular formula, that is the carboxylic acid group, and that's very commonly sometimes, you know, how it's written, kind of shorthand. So that's going to also give us pentanoic acid here. And here, this would be carbon 1, 2, 3, 4, and 5. That means at 3, we have a chloral group. And at 4, we have a methyl group, right? So 3 chloral, 4 methyl pentanoic acid. Yeah. Any questions on that one? Obviously, alphabetical like normal. And again, we're numbering with that carbon oxygen being number 1 always, no matter which side it's on. So a lot of times it's drawn to the right there, but obviously if it's on the left-hand side, that would be carbon number 1, whichever side you draw it on. Any questions on that? All right, so why don't you give the names for these guys and see what you come up with. Carbon chain, we do need the carboxylic acid group being part of it. And that looks like 3. Once again, you could also get 3 if you go straight and then up as well, gets you 3. So 3 is based off of propane. And again, we have the carboxylic acid group there at the end, which tells us it's going to be propanoic acid. Here, this would be carbon number 1, this would be carbon number 2, and at carbon number 2, we do have a methyl group, so a 2-methyl propanoic acid. Any questions on that one there? Looking at the one on the right here, got a lot going on, but really, we got one big thing, all is basically the same thing. We have a benzene ring that has that carboxylic acid group attached. So that all is basically one thing, and that is our, I'll go down here, benzoic acid. And because where this functional group is attached on the ring, that will be carbon number 1. We do have a BR there, so we do want to give it the smallest number, and you can probably see going clockwise will do that for you. If you went counterclockwise, you would end up with a much larger number than 3. Obviously, you get 5 if you went the other way. So this would be 3-bromyl benzoic acid. Any questions on those there? Yeah. Yeah. No, in terms of the name for the benzene part, or no, you don't, because that is basically the name of it, the benzene ring. Because remember, the benzene ring is the one that has 3 double bonds in it. And if you don't have 3 double bonds, then that's just cyclohexane, for example. If you have just 1 double bond in there, that's going to be cyclohexene. And even with this guy, you wouldn't have to get a location where that's at, but it would be carbon 1, just kind of like the other group would be for the numbering of everybody else. Other questions? All right, why don't you draw 4-chlorohexanoic acid? Why don't you also draw, I don't know, let's do 4-ethyl 3-methyl butanoic acid. Actually, let's do that. I'm just going to change the numbers though, since I changed my mind at the last minute. We're going to do 3 and 2. We'll do 3 and 2. Take a look. Once again, we're going to draw backwards in the name. So oic acid tells us it is the carboxylic acid group that we are dealing with. And kind of the hexane part tells us it's 6 carbons. So you could go with the 6 carbons here, 2, 3, 4, 5, and 6. Again, because you're drawing it, you can really put that carboxylic acid group on either end. It doesn't really matter, but it does have to go on the end. So I'll put it here. And because I did put it there, that would make this carbon number 1 for me, which is important because my carbon number 4 would be right about there, I believe. And that is where we're going to have a chlorine. And that will take care of pretty much the name here. And we will go with that and some hydrogens here as well. This obviously is a condensed formula. If we want to do the line structure, we would do the same thing. Basically, we'll start with the 6 carbons, 1, 2, 3, 4, 5, and 6. Remember that we do have to kind of draw it down, put the OH, and also put the double bonded oxygen there to the carbon. And this should still be carbon 1, 2, 3, 4, 5, and 6. Now we'll just place what we need, which is that carbon number 4 here. And we'll put a Cl there. Yeah. Any questions on that one there? Remember, you do need to draw if you're going to do line structure, obviously, all those things in the actual picture. You can't just leave them empty. Otherwise, it's assumed to be carbon. So you got to put all those guys in. Question on that one there. Coming this way here, oic acid still tells us carboxylic acid. Butane is 4, so 1, 2, 3, 4. Again, you could put the group on either end. I'm going to put it back over here. And again, because I did that, that's going to be carbon 1 for me. And that means at carbon 2, I have a methyl group, which would be there. And at carbon 3, I have an ethyl group, which would be here. And now we're just going to hydrogen it up here as we're done with everything else. So yeah, we'll do an H and an H squeezed in there, I think. And then we should be good. Again, you're going to take the same approach you do line. You're just going to start with the 4, 1, 2, 3, and 4. Once again, you do need to kind of draw it down to complete the group there. And that would again be carbon 1, 2, 3, and 4 here. And here at number 2, we have a methyl, which means we're just going to draw a line. And at 3, we have an ethyl, so a little line actually like that to give us 2 carbons. Any questions on that there? Okay. All right, so obviously we drew some there. Yeah, obviously you need to be able to draw them and name them. Let's talk about some of the properties here of carboxylic acid. Carboxylate salts are often used as preservatives. And salts are really carboxylic acids that have lost that hydrogen off of the OH group part of it. And that's what you can kind of see here. We will lose some of that H plus, and it will basically become a salt. But a more important property of a carboxylic acid, as I mentioned earlier, is really it contains 2 polar groups. And these 2 polar groups are really important for how it's able to interact, say, with something like water. So it's able to interact really well with water through both of those polar groups, actually. And in addition, it is one of the few things that can beat an alcohol in terms of boiling points and melting points because it has both of those groups. So up until this point, in terms of boiling points, melting points, really your alcohol has been your champion in terms of highest boiling points, melting points. but it is a carboxylic acid because it has both of these sort of groups. It can actually bond with itself in 2 locations. It can hydrogen bond with itself through 2 locations. And what that does is create a pretty strong bond with a carboxylic acid in itself, and it will actually have the higher boiling point and melting point because of that. Would be your carboxylic acid because of the ability to really make what is sometimes referred to as a dimer. It's able to kind of bond with itself through those 2 spots, basically do a little hydrogen bonding action, at both of those places. So it makes a really strong attraction between them. And so highest boiling point here and melting point would go to our carboxylic acid. So it's one of the, like I said, one of the few things that could kind of be in an alcohol in terms of those polar groups. It also will allow it to make hydrogen bonds with water very easily. Again, water could hydrogen bond at the carbonyl group, the oxygen there. And that's right here. That's the carbon-oxygen double bond. It's able to hydrogen bond. It could also, again, hydrogen bond at the OH group on the carboxylic acid. So that gives something like water a lot of places to interact and hydrogen bond with a carboxylic acid, and it makes it fairly soluble in water. And like most things that are soluble in water that are organic, it kind of tops out, even though it has these groups at about 5 carbons or less are really soluble in water. Again, as you get a lot more carbons involved, as we talked about, it just sort of gets in the way of the interaction with water and makes it less soluble at that point. So because it has this ability to do so, 5 or less carbons will be really soluble in water. That's why if we take some acetic acid like vinegar and water, it will mix because it will be soluble in water. They're able to hydrogen bond with each other. So as you can see here, soluble, 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 all the way to pentanoic acid. Right about 6 or so carbons, you start getting slightly soluble, which basically means, for the most part, more insoluble than soluble. So it starts to decrease a lot, even though it has these polar groups. That non-polar part of the molecule is starting to become bigger and bigger, and frankly, just kind of gets in the way of everything working really nicely with it. Now, because they are acids, they basically react like acids and they behave like acids. Most carboxylic acids are weak acids. If you remember, weak acids are ones that stay together. They don't fully break apart, but they will break apart a little bit into water and produce H plus and whatever the ion part of it is. So for example, if you took acetic acid in water, it will react as an acid, which means, as we know, it is this hydrogen that will be donated over H plus, basically a Bronsted-Lowry acid-base definition. And it will make this guy here, which is basically acetate. And it will make H3O plus, which, as we know from our acid and base chapter, that is why it's considered an acid, because it has the ability to produce H3O plus in water. Acetate is what they refer to as a carboxylate ion. That is acetate in this case, is basically what it means. It's the carboxylic acid less 1H plus that came off is what's referred to as a carboxylate ion. It's kind of what we used to call a salt part of it, like the salt and water kind of thing. It's a salt part of that. And that's what we see here on the bottom. It makes an ethanoate ion. You don't have to name the ions, but it will basically do a pretty much Bronsted-Lowry acid-base definition and reaction. Going to send over an H plus as I drew up there on top. And it's always, by the way, the H that is attached to the OH. That is always the hydrogen that gets basically treated as an acid part. That's the H plus that basically comes off. So we want to write a balanced equation for dissociation of butanoic acid and water. So we'll start with butanoic acid. We know that is 4 carbons. Oic acid means that there is an OH group on it there with our carbon-oxygen double bond. We'll put in our hydrogens. And dissociation with water just basically means it's going to break apart in water. But again, you could look at it as we just talked about as the Bronsted-Lowry definition. So it's going to be this H from our acid going to be donated over. Remember, as we talked about an acid base chapter, the H is the H plus, the positive part of it's coming with. And that's important for what is left over, which is everything's exactly the same except you get rid of the H plus. And when you lose an H plus, you become one more negative, which is why that guy ends up with a negative charge in that case. And obviously our H2O will gain the H plus and become one more positive. So it's pretty much the same reaction we saw in the acid base chapter with this acid dissociating. Again, it has the two arrows because it really is a weak electrolyte. It mainly stays together, but it will form a little bit of this in solution. And because it's able to form H plus or H3O plus, that is why it's considered an acid in this case. Any questions on that there? Go. Now, it can also, because it's an acid, do a traditional acid-base reaction as well. So if you remember when we talked about acid and bases, you take an acid, which is this carboxylic acid, you take a base like sodium hydroxide, you get a salt and water, basically. And the same thing happens with these as it did in the acid chapter. The water is made from the H from the acid, and the OH from the base. There's going to do a double displacement reaction basically, and that is where the water comes from, those two parts right there. And the salt part comes from the other part. These two guys come together basically here. So this is still a double displacement reaction, this guy being negative, the H being positive, this guy being positive, this guy being negative. Again, the two positive guys switch partners and you make water basically with what's left over, and you get your salt on the other side here. That is basically this part of it here. And a salt is, again, just an ionic compound. So a positive guy, negative guy here along here. Any questions on that there? So because these are acids, it could basically dissociate in water and do sort of the Bronsted-Lowry definition. Because they are also acids, they can react with a base and do just a basically double displacement reaction like we talked about in the previous chapter. And again, you'll always get water, H plus from the acid, OH from the base. The other two parts that are left over come together to make the salt part of it in this case. So the carboxylate ion is named by replacing ic acid with 8, and we're not going to do that, so you don't have to worry about naming the salt parts of it. But just a little bit about those salts. They are ionic compounds. They're held together by those electrostatic attractions. They are solids at room temperatures, and because they're ionic compounds and they're held together by that intramolecular force, that ionic interaction, they usually have very high melting points. They're also usually very soluble in water because they are ionic. So ionic things in water, which is polar, are usually very good with each other and very soluble in one another. Now, as I mentioned before, their carboxylic acid salts are used as preservatives. So here's some of the examples of them. Sodium propanoate used in cheeses. Monosodium glutamate, MSG, is added to meats, fish, and baked goods to enhance flavors. And sodium benzoate is used there in fruit juices, margarines, and relish. So we want to write the reaction here between propanoic acid and sodium hydroxide. So again, let's take a look at it here. We'll start with propanoic acid. So we just want to draw what we know it should be. So propane is 3 carbons. Oic acid tells us it's the carboxylic acid. So we'll draw our carboxylic acid. Is going to react with sodium hydroxide. So basically here we have an acid and a base. So as we talked about, one thing that we know we should get when we put those together is water. So we know the water should come from the H from the acid and the OH from the base, right? So that's going to get us our water part. Just make a little box here to write it. And when we do that, that will obviously form our water. Now the salt part is going to come from whatever's basically left over. So whatever's left over, this is really a positive guy now, and this is a negative guy. So they're going to come together and basically make that salt, and nothing's going to change. It's just going to pop these guys together, basically. So you'll have CH3, CH2, C double bond O with a negative. I ran out of room, I'll just put it underneath, and you will have a sodium with a positive charge to make this ionic compound right there. Any questions on that? This is really just a double displacement reaction like we saw in the previous chapter, just with our organic guy drawn out this time rather than just the molecular formula of it. Any questions on that there? And obviously, that's all the green guy, right? All right. So carboxylic acids in metabolism, they are part of metabolic process. They're used during glycolysis as a molecule of glucose is broken down into pyruvate and a carboxylate salt. During strenuous exercises, pyruvate is reduced to give lactic acid or lactate ion. So again, we have our carboxylic acid, and still here in lactate acid, we still have our carboxylic acid that's present. Also in the citric acid cycle or the Krebs cycle, you see these guys. Again, as I mentioned before, very commonly, this is how the carboxylic acid group is sort of written in formulas. So again, when you see that, that is the carboxylic acid group there. That is that guy right there, that arrangement. All right. We'll talk a little about esters, and esters have a functional group that looks like this. Kind of looks like a carboxylic acid attached to a carbon at the end there and not a hydrogen. And that is because, as we will talk about, that is how you get it. You take a carboxylic acid and you take an alcohol and you slap them together basically, and you get an ester. So they have a little bit of some of the both of those groups, kind of an alcohol part and also a carboxylic acid. So as we will see here, you take these guys and basically you take out water and you just squish everybody together and you get your ester in this particular group. So esters are forerunners, for example, like aspirin, for example, is an ester. Salicylic acid is part of it. So esters are synthesized through, as I mentioned before, a carboxylic acid and an alcohol. This is what is referred to as an esterification reaction. An esterification reaction is basically making an ester. And again, you basically just take that carboxylic acid, you take that alcohol, and you basically take out water. And when you do, however you want to take out water, remember whatever way is easiest, and then you basically just squish everybody together to give you that ester connection that is always this. And that's why it's connected here to a carbon at the end, unlike the carboxylic acid that has a hydrogen, because that hydrogen is now gone with water. And now the next guy that's coming in is the carbon. They're really from the alcohol in that particular case. They're found in fats and oils. They're responsible for a lot of aromas and flavoring like bananas, oranges. I think you might do that in lab this week. put them together and smell. Don't smell too much, I suppose. So this esterification reaction, as you can see here, we're just going to take our carboxylic acid and our alcohol. So it doesn't really matter. And this, you just want to keep it kind of simple in terms of how you can figure out what you're going to sort of draw. So what you want to think about is, in this case, I would recommend kind of turning your alcohol around so you could kind of line it up so you can see where the water's coming from. And you basically just got to take out water. So you could put a box around it, you could highlight it, whatever you want to do. But basically, these two guys are going to come out, and that's going to make water. And once you do that, pretty much all you have to do is copy what's there. And that's why I would recommend kind of aligning everything in the correct orientation so that when you squeeze it together, you have it in the right sort of way. And basically all you have to do is copy what I just highlighted in green, and you will get this and this. And that would be our ester here. And again, our functional group of our ester is right there, basically, in that particular case. So if you remember the ester connection, basically carbon-oxygen double bond to an oxygen, just orient your alcohol in the right orientation, take the water out, just squeeze them together, copy left to right, and you'll have basically your product there, as you can see here. So how do we go about sort of naming these guys? Well, because there's really two parts to the ester, there's an alcohol part and a carboxylic acid part. The alcohol part is really this part of it. And going towards the carbon-oxygen double bond is our carboxylic acid part. And the alcohol part is named as a group. So the carbon group that's in there, as we can see, is just a one carbon group, and that is a methyl group. So that is where the methyl part of the name comes from. The carboxylic acid part is named based off of how many carbons there are, which is one carbon, two carbons. That's based off of ethane. We do drop the E and add OH to it. So this is known as methyl ethanoate. Again, the alcohol part gives you kind of the group name, and the carboxylic acid part gives you the base of the name, and we draw a pop O8 at the end of it there. Question on that there. So here's another example of the esterification reaction. By the way, you will sometimes need H+, which is an acid catalyst, to help it along, and some heat, which is sometimes abbreviated with a triangle here, right? And this is what we see in pairs. Once again, we're just gonna box out our water, and what is left is gonna be basically squished together. So we have this guy left after the water, and we have this guy, which, so when we put it together, we draw it exactly squished together with the water out of it. And we do end up with that right there. Now, again, if we're going to name this, we want to think about where it breaks apart. So between the carbon-oxygen single bond is where we have our alcohol part. So with the O carbon group there, that's the alcohol part. Here, this is the carboxylic acid part. So when we look at the alcohol part, there's one carbon, two carbon, three carbons on it, and a three carbon group is propyl. The carboxylic acid, one and two carbons, and that's based off ethane, and that is the one that gets the O8 at the end of it. So this would be known as propyl ethanoate in this case. Question on that there. So why don't you try one here? What is the product here? Let's do All right, so draw the product, and why don't you also give a shot at the name of it as well? Okay, so let's take a look. So first off, you identify what you got going on. We have definitely a carboxylic acid, and we have an alcohol. So you should know that when you put those two together, you get that esterification reaction. And basically what that means is we're going to take out water, basically. So we want to, again, probably rearrange our alcohol here just to make it easy on yourself so that you do get the connection. So what I'm going to do is just going to redraw this guy facing the other way with my hydrogen facing my carboxylic acid. And we'll just kind of turn this guy around. Now, the reason I want to do that is now also remember is take out water, and however you want to choose to take out water, it really won't matter in the end, but you know, I could just put a box around basically the water part of it. So that would give us obviously water here as our product. And now the reason we rearranged it like this is should now make it in the right orientation to draw it. All we have to do now is just draw everything outside of the water and squish them together basically to make our connection. So again, when you load to draw these things, you pretty much have the answers staring at you here on the question. Don't be afraid to copy the question, right? So make sure you change something, but most of it is exactly the same. So again, pretty much I just copied exactly what was there. I have now taken this out, so I'm going to pick up back over here, and that's going to give me my ester connection that I need right there. And off we go with the rest of what's on the right-hand side. And now I have my entire ester drawn here. Any questions on that one there? Now the naming, you just also want to keep it simple for yourself. You know they come together right here. So just, you know, draw a little line there between those. And going away from the double bond will always be the alcohol. So always going away from the double bonded oxygen there is the alcohol. Going towards the double bonded oxygen will always be the carboxylic acid part. So again, that's the way you could always sort of organize it in your head. And what that means is it's the alcohol part that gives us the first part of the name, and that is 2 carbons, which means that is an ethyl group. So we're just going to name it like a group. And then for the base of the name, we're going to go to our carboxylic acid side. 1, 2, 3, 4, and 5 carbons. So that's based off of pentane. We'll drop the E, and this guy gets the O8 attachment, not the ic acid. So ethyl pentanoate in this case. Any questions on that there? All right. So why don't you write the balance equation? Okay, so let's take a look. Again, we have propanoic acid, which is a carboxylic acid. We have methanol, which is an alcohol. So again, and it will help you out if you understand. You take carboxylic acid and an alcohol. That is going to get you our ester in this esterification reaction. And again, we're basically just taking out water as we talked about. So when we draw these, we kind of want to line it up so everything works out nice. So propanoic acid is again 3 carbons. Oic acid is our carboxylic acid. So you can really put it on either end. So I'm going to put it here to the right because it's going to line up nicely with my alcohol, which is methanol, which is actually only 1 carbon. So again, I'm going to put my OH group pointing towards the other OH group. That way everything will line up correctly. So if you just kind of go OH to HO, you'll have it in the right orientation for this. Once you do that, you're ready to go. Again, you can just throw a box over your water part, which you know should come out. And at that point, all you have to do is go left to right because of the way you organize it and basically just copy exactly what's there and connect them up. So that will get you, I'll go underneath here, CH3, CH2, and C double bonded O. That takes care of everything on this side. I'm going to make my connection to the right-hand side here, which will give me my ester bond, And now I have an ester that is here in front of me. Any questions on that there? Now we want to name it. So once again, understanding the ester and how it comes together, we once again know that if I always gonna kind of put it together right there. Again, if you go away from the oxygen double bond there, this way away from it, that is your alcohol part. And if you go towards the oxygen double bond, then that is your carboxylic acid part. So it is our alcohol part here that gives us our group name. Since there's just one carbon, a one carbon group is methyl. It is our carboxylic acid part that gives us the base of our name, which is 3, also based off of this guy. And that means it's going to be propanoate, and this would be methyl propanoate. Any questions on that there? So again, understanding what you get when you put those together can be really helpful when you go to draw it, and understanding what leaves, for example, also very helpful in terms of lining it up. Any questions on that? And understanding obviously our ester connection here. So just in case you don't line them up correctly, you should understand that that is the connection, and not what a lot of people might try to do, which is, if you didn't line it up, say that way, try to connect in this way, right? So you don't want to connect the wrong way. So sometimes just turning it to begin with puts everybody in the right orientation so everything gets connected correctly. Any questions on that there? All right, let's take a 5-minute break. Come on back. Let us continue on here. First off, any questions on the reaction we just did? By the way, if you're going to, say, draw your product there in a line structure sort of formula, you would do kind of the same thing. You go up, down, bad draw, 1, 2, 3 carbons. And then you would have to put the O in there, and obviously the double bond. So look, maybe something like that along the way. So yeah. As long as it's on the right hand side. As long as these things are, technically speaking, on the correct side of the arrow, it doesn't matter which one comes first or second, really. Yeah. Other questions? Okay. All right, so we kind of touched upon naming it as we were doing those. So as I mentioned, there's really 2 parts to our carboxylic acid, which is the carboxylic acid part and the alcohol part. So there's 2 parts to our ester is what I was trying to say there. There is the alcohol part and really the carboxylic acid part. And as I mentioned before, however you want to think about it, but if you want to think about the break apart right there, and again, always going away from the carbon oxygen double bond will give you your alcohol part, and always going towards it will give your carboxylic acid part. So obviously here we have that 1 carbon group, which is our methyl. And again, here on our carboxylic acid part, we have our 2 carbon group, which gets the O8 part of it, and that gives us our methyl ethanoate here. So some esters do have some common names, and we're not going to worry about the common names for these guys here. But again, just to look at the naming here, if you're not sure, you look at the ester, it's got to be there. Going away from the double bond is our alcohol. Going towards the double bond is our carboxylic acid. So this part's going to come first, so that's the ethyl part. And again, here 2 carbons is the ethanoate part on that particular one there. Again, if you break it right there, away from the oxygen double bond is the alcohol part. Towards the oxygen double bond, carboxylic acid part. 1 carbon group, methyl. 1, 2, 3, propane with an O8 at the end of it. So methyl propanoate. And here we actually have a benzene ring popping in there. So again, right about there, away from the double bonded oxygen is our alcohol part. This is our carboxylic acid part. So 1, 2 carbon group is ethyl. And again, this is benzene, so O8 at the end of it, so benzoate. So ethyl benzoate here would be our ester name. And that again is the way you just kind of want to think about it if you have the ester there and the different parts of it and how to put it together. Any questions on doing that there? All right, so as I mentioned before, some of these esters are precursors to sort of aspirin, if you will. And as you can see here, we have basically a carboxylic acid here. And and an alcohol part here on salicylic acid. So these guys are going to come together, take out the water, and now we have our ester connection right there, basically. Is our ester connection, which is basically the main part of aspirin. Years ago, they used to let you make that in chemistry classes. Not so much anymore. Oil of wintergreen, which I think may be one of the ones you make in lab this week, is used for skin ointments. And again, it's going to be our salicylic acid here with our OH coming into our, I'm sorry, I wrong shot there. It's going to come this way. Our carboxylic acid and our alcohol there are going to come together. And again, making our oil of wintergreen there, which is our name there. As you can see, it is based off of really salicylic acid, so has a little bit more going on in terms of that name. But here's our ester connection right there. All right, so why don't you name this guy here? Why don't you also name this one as well? Okay, so let's take a look, and again, hopefully you could recognize the functional group there. That's the ester right there, and that is the ester group right there as well. And again, once you identify as an ester and you have the picture, my recommendation would be like we've been doing, just draw your line right there and identify the two parts to it. And again, going away from the double bond will always be your alcohol, and going towards the double bond will be your carboxylic acid. So starting with the alcohol part, which gives us our group name, we basically have 2 carbons. So that's going to be an ethyl group. And our carboxylic acid, 1, 2, and 3 carbons. And that's going to be based off of propane. And again, we're going to drop the E and put the O8 at the end of it, and a little ethyl propanoate. Any questions on that one there? Even in line structure, you still want to do the same thing. Again, the connection is right there. Still going away from the double bond there. Going to be your alcohol, going towards it, going to be your carboxylic acid part. So in this case, going our alcohol part, we got 1 carbon, 2 carbons, and 3 carbons in that case. And that's going to give us a propyl group. Looking at our carboxylic acid, we got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and lucky number 6. Going to be based off a hexane. Going to drop the E and put a little O8 at the end of it. And we got a propyl hexanoate. Any questions on either of those there? Huh? All right. So why don't you give this, and why don't you also draw a couple of them here? So why don't you draw, let's do something. Let's go ethyl octanoate. Let's do pentyl butanoate. All right, so draw those 2 in addition to naming the one on the bottom there. Okay, so let's take a look at the first one on the bottom. We'll do their naming. So again, I'm going to recognize hopefully our ester group there. And if I need to name it at this point, I'm just going to draw a little line. And again, going away from the double bond, my alcohol, and going towards the double bond, my carboxylic acid. So starting with our alcohol group, that is 3 carbons. So that's going to be a propyl. And our carboxylic acid, 2 groups. So that's going to be based off of ethane. And it'll get the O8 at the end of it. So propyl ethanoate. Any questions on that one there? All right, so now we're going to draw, and we're going to still kind of work backwards, but maybe slightly different approach here. So when I go backwards, I see O8, which tells me it's an ester, and octane there is 8, and ethyl is 2. So in this case, kind of like what we did perhaps with like the ethers and so forth, I'm going to actually just start with kind of like the functional part of it. So I know the O8 part means that I have a carbon-oxygen double bond attached to an oxygen. And as we've been talking about, as we go away from the double bond, that is where our alcohol part comes from, and that is our group part of it. So in this case, that's an ethyl, which means I need to attach 2 carbons to it, right? Now going the other way towards the double bond, that's our carboxylic acid part, and that's really where this part of the name comes from, and that's octane. Now I regret it. That is 8 carbons there. I do have to remember though that I already have 1 right there to begin with, right? So I don't want to put 8 more. I just need 7 more actually at this point. So 2, 3, 4, 5, 6, 7. How much total? 1, 2, 3, 4, 5, 6, 7. And we'll go down. 8. We'll just go down that way. And at this point, everything else can be hydrogen. So we're going to do a hydrogen there. We'll do 2 there. We'll do 2 there. We'll do 2 there. 2 there. 2 there. 2 there. 2 there. And since I had to go down, I ran out of room. We'll go 3 there for our guy at the end. Any questions on that? So here I would probably start with the kind of functional group to draw it. Same thing here. The O8 here will tell us it's a ester, and that is where I'm going to start with, which will be our, I'll go right up there, maybe. And once again, going away from the double bond is going to be our alcohol part, which is this part. So that's pentyl, which is 5. 1, 2, 3, 4, and 5, squeezing it in. And going the other way is butane, which is 4. I already got 1. So 1, 2, 3, and 4. And obviously at this point, everything else is going to be hydrogens here. Obviously here, 2, 2, 2, squeezing it in 2. And there should be 3 there. So let me redraw it up here a little better, I think. Pop it right there, I think. I can actually see it. So 1, oops. 1, 2, 3, 4, and 5. And I go the other way. 1, 2, 3, and 4. So let me fix my bad oxygen there. Any question on those there? Obviously, if you're still doing, if you want to do line structure, same idea. I would, you know, kind of start with your connection, and then obviously you could do whatever you need, like 1, 2, 3, 4, 5, and then coming this way, 1, 2, 3, and 4. There you go. Any questions on drawing, naming esters? All right, so as I mentioned before, they're responsible for a lot of fragrances and flavors that we see. Many of them are in perfumes and flowers are due to these esters. Small esters are very volatile, which means they go into the gas phase really easily, which is why they're responsible for a lot of fragrances. They're also soluble in water, so we can taste them. Again, small esters, not really big ones, because they have that carbonyl group. Water is able to hydrogen bond through that carbonyl group, The ester itself can't hydrogen bond, but the oxygen there allows the hydrogen from, say, water to hydrogen bond with them. So here's a table of some of the ones there, like pears. We have our propylethanoate, bananas, our pentylethanoate, oranges, our octylethanoate, pineapples, and apricots, ethyl butanoate and pentyl butanoate as well. Okay, so looking at the first one here, we see oic acid, which tells us it's the carboxylic acid. So that is this group there. And the butane part tells us it's 4 carbons. So we'll go 4 carbons. Again, you could put this group on whichever end you like. So I'm just going to put it over here. Because I did put it over here, as we talked about, that definitely will have to be carbon number 1. Obviously, if you put it on the other side, your carbon 1 would be on the other side. That would take care of basically this part of it. And at carbon number 3, we have a bromine. So carbon 3 would be right about there and a Br. And now we just need to fill in our hydrogens like normal here. And there we go. Yeah. Any questions on that one there? Looking at this one, that's O8, which tells us it's an ester. So it's got this connection. So as we just talked about, I would probably start with that connection and kind of work your way out from it. So kind of do that. And once again, the ethyl part comes from the alcohol part, which again should go away from the double bonded oxygen. And ethyl is 2 carbons, so 1 and 2. The propane part is for the carboxylic acid, which should go in that direction. And that is 4. Remember, I do already have one. So 2, 3, and 4. And now at this point, we're just going to put in our hydrogens there to get carbon to 4. And a couple there and there. Yes. It is. And I just want to make sure you're paying attention. It's not butanate. I don't know. All right. Well, that's good. Well, it's good why they invented erasers, I suppose. There you go. There you go. How's that? That looks better, perhaps. I hope. There we go. All right, I got carried away. It's all right. It happens. All right, so there you go. Thank you. There should be obviously 3 carbons based off of propane in that case. Yeah. Other questions on that there? All right. All right. Questions on how to draw these things, name these things. Obviously, you need to be able to do both. Yeah. All right. So we talked about how we make esters. Let's talk a little bit about some reactions esters undergo. And these are hydrolysis reactions. And hydrolysis basically means water is involved. So kind of these reactions are the opposite of putting them together. So as we saw when we put them together, we take water out. In these hydrolysis reactions, we're going to kind of put water in a sense. And there's 2 types of hydrolysis reaction. There's an acid hydrolysis and also a base hydrolysis. So we're going to start with the acid one. So in the acid hydrolysis, we know it's an acid hydrolysis because we got a little H plus action happening there. Also, it's a hydrolysis because we have water. So the acid one pretty much is the exact opposite of the esterification reaction. So in the esterification reaction, we took out the water. So in the acid hydrolysis reaction, we're going to actually put the water back in. So when we do this, what we're going to do in the acid hydrolysis is simply, obviously, we do need to make some room for that. So we got our water here. So just like we name it and everything else, you could think of it as just breaking apart there. So we're just going to break it apart right there, how we put it together. And what I would do in this case is just simply draw the 2 parts separated because we are going to break them apart in this reaction. And again, you could have something like this. And now really what we're going to do is basically just kind of use water to rebuild what we should have started with. So we know this is from a carboxylic acid and an alcohol, right? So in order for the guy on the left, which comes towards the double bond, to become a carboxylic acid, it needs an OH, so that goes away. And that means that the guy on the right is our alcohol. In order for it to become an alcohol, we need the H. So this is basically the exact opposite of making an ester, is basically breaking it back into both the carboxylic acid and the alcohol. So you'll get both guys exactly the way it is here in the acid hydrolysis. The reason you really get both of them back in the acid hydrolysis is because there's acid involved. So there's that extra H plus that's there that allows it basically to get back completely what you started with. So again, you can think of this as basically just the exact reverse reaction to making an ester, is basically taking it back apart. Any questions on that there? Now, the other type of hydrolysis a ester undergoes is what's known as a base hydrolysis. And in a base hydrolysis, sometimes referred to as a saponification reaction, which is really a fancy way of saying soap, basically. Is basically this reaction is the reaction that's used to make soap. In this case, it's a base hydrolysis because kind of instead of water, we're using a strong base. And because we're not really using water here, we're actually not going to get back both things completely. So we're not going to get the carboxylic acid and the alcohol back like we do in the acid part of it. But we will get one of those. And the one thing that we get is actually the alcohol. So we get the alcohol back, but we do not get the carboxylic acid back. So you could kind of think of it this way as well. And again, it's not perfectly exactly how it happens, but for our purposes, it's good, I think. We're going to take this and we're going to add basically sodium hydroxide here. And we could add sodium hydroxide as like H and like an O, Na here, right? And this part of it here is going to be kind of negative, and this guy is going to be positive. So once again, we're going to break it the exact same spot. So we're just going to break it in the exact same spot. And we're going to draw our pieces basically here. And in this reaction, as I mentioned before, we do not get back both parts of it. We actually only get the alcohol back. So to get the alcohol back, we will need the hydrogen. Now, what that leaves us is basically an oxygen and a sodium in this particular case. And what makes a carboxylic acid, right, is this. And what makes a carboxylic acid salt is this. And the connection is the carbon to the oxygen. So that is how we would want to do it. It's actually this guy that's negative, and there's a sodium ion there that's positive. This makes one of those carboxylate salts that we talked about. And we don't get the complete carboxylic acid back. We basically get that salt. But the important part of the connection is it should have the oxygen connecting in to the carbon. Makes almost like a carboxylic acid there part, functional group, without the hydrogen in that case. And this is, again, as I might have mentioned earlier, basically what soap is. Soap is a much longer part here. That's a bunch of carbons and hydrogens there. And this is a polar part of soap. And that's the reaction that occurs. So why don't you try each of those and see what you get? If you started with methyl ethanoate, what would be the result of the acid hydrolysis? And then the bottom one, what would you get in the base hydrolysis? Let's see what you come up. Okay, so let's take a look and see. So we want to start with obviously what we're starting with, which is methyl ethanoate. So the O8 tells us it is an ester. So we got this guy coming here. The methyl is a 1 carbon group there for our alcohol side, and the ethanoate is a 2 carbon group. Since we already have a carbon, that is what we're starting with. Now, in the first one, we're doing water, heat, and an acid catalyst, which sometimes is abbreviated in problems as H+. So remember the acid here, we're going to basically add water. And if you want to remember it this way, acid all. So we get everybody back. We get all of it back that we started with. It's a good way to remember that. And so at this point, what you just got to do is just break it up where we've been talking about, which is a good place to do this. Draw the 2 parts. Again, obviously here we're going to break it apart, so you want to separate those parts. And since you want to remember it perhaps acid all, you get back everything you started with, which is a carboxylic acid and an alcohol. So obviously to make our guy a carboxylic acid, we would need that. And to make our guy into an alcohol, we would need that. That gives us our methyl ethanoate to our ethanoic acid and our methanol, right, in that particular case. Any questions on that one there? Now, the bottom one, which is a base hydrolysis, still starting with the same guy. So we'll draw our exact same starting point here. In this case, though, we're not going to add the water, but we're going to add a strong base. So if you want to remember what you get back on this, it goes with the base, the OH part, which is the alcohol, right? So you can kind of think of that as the part that you get back. We're going to break it apart in the exact same spot. Going to give us our two parts again. And our OCH3. Remember, though, that in this particular case, the only thing that we get back is the alcohol completed. And again, that's sort of how you can remember with a strong base. OH is in there. It's like an alcohol part, right? So that is what comes back. If I draw my H really badly there. There you go, my bad H on there. Now, what that does, if you just kind of scribble it out, it leaves you an O and a K. So remember that a carboxylic acid, a carboxylate salt has a carbon-oxygen connection. So that O has to be connected to the carbon there to make it like a carboxylic acid. And it will actually have a negative charge, and that potassium will have a positive charge, and it will make basically a salt. It's basically potassium ethanoate is basically what it just makes there in that particular case. So we get this salt here. We do not get back both of them. Only in the acid hydrolysis, we get back both of them. So again, acid all, you get them both back. And the base one, you get just the alcohol. If you want to think about the OH part, guy back only is what you get back. Any questions on those there? No. Question on esters are carboxylic acids. All right. I think we will lay it up there for